On September 26, 2022, humanity did something no civilization had ever attempted. We aimed a spacecraft the size of a vending machine at an asteroid and hit it, on purpose, at 14,000 miles per hour. The goal wasn't to destroy it, it was to nudge it. Just physics. No explosions, no magic. Segment 1. The setup. That test run traces back to 3 rules one man wrote down in 1687 and never left England to prove. If a killer asteroid ever heads for Earth, we now know we could shove it out of the way. And it all comes down to Isaac Newton. Segment 2. The science foundation. Newton's first law. An object at rest stays at rest, and an object in motion stays in motion, unless something pushes on it. That's inertia, the reason you lurch forward when a bus stops short. Your body wants to keep going, even after the bus decides not to. Second law. Force equals mass times acceleration. Push something heavier, and you need more force to speed it up the same amount. It's why a shove that sends a soccer ball flying barely nudges a boulder. Third law. The one that mattered most on impact day. Every action has an equal and opposite reaction. Push on something, and it pushes back exactly as hard. A rocket doesn't fly because it pushes against air. It flies because it hurls exhaust backward, and the exhaust hurls the rocket forward, just as hard in return. 2 more forces shape almost everything Newton described. Friction is the drag between surfaces in contact. It's why a hockey puck slides for meters, but a book on carpet stops almost instantly. And centripetal force is what keeps anything moving in a circle from flying off in a straight line. The tug of a string on a swung ball, gravity holding the moon in orbit, the wall of a spinning fairground ride pressing you inward. None of these are separate stories. They're one system, always operating together, which is exactly what NASA needed to lean on when it came time to move an asteroid. Segment 3. The recent research anchor. That asteroid was Dimorphos, a moon orbiting a larger asteroid called Dimorphos. Neither one threatened Earth. This was a rehearsal. NASA's DART spacecraft smashed into Dimorphos at roughly 14,000 miles per hour, and the mission's core question was pure Newton. How much momentum transfers from a small, fast object to a much larger, slower one? The result, published in Nature, was better than anyone hoped. Scientists measured an instantaneous drop in Dimorphos's along-track orbital velocity of 2.70 millimeters per second, showing the impact transferred far more momentum than a direct hit alone would explain. The extra push came from debris. Rock and dust blasted off the surface on impact, flying backward and shoving the asteroid forward even harder, exactly the way exhaust shoves a rocket. Researchers call that the momentum enhancement factor. Their measurements put it between roughly 2.2 and 4.9, meaning the ejecta alone did 2 to 5 times more work than the spacecraft's body slam by itself. Follow-up papers went further. Based on how Dimorphos's orbital period actually shifted, researchers calculated the change at about 33 minutes, nearly 5 times larger than the roughly 7-minute shift a simple, no bounce-back collision would have produced. One spacecraft, one collision, one very old law from 1687, and an asteroid's orbit was rewritten, just as the equation said it would be. Segment 4. Closing summary pulse teaser. So that's the quiet power of Newton's laws. They're not dusty classroom equations. They're the same rules running a bus stopping short, a hockey puck sliding to a halt, and a spacecraft nudging an asteroid off its path through empty space. 3 centuries after Newton wrote them down, we're still using them to defend the planet. Next episode, we're heading back underground into the science of earthquakes and why some cities can predict the shaking seconds before it hits. I'm David. Thanks for listening. Stay curious.